In 2004, two archaeobotanists published findings from a Roman cremation grave in central France. The site, located in the volcanic basin of Limagne, had been buried for close to 2,000 years. What Laurent Bouby and Philippe Marinval were examining was not gold or weapons. They were studying seeds. Among the charred plant remains placed alongside the dead, they identified the expected offerings: lentil, pea, faba bean, foods that make sense in a ritual context. But there was something else in the ash. Another legume, deliberately placed, burned with the body, not discarded near the grave, not waste. In Roman funerary practice, what entered the fire was chosen, and someone chose this plant to accompany the dead into the next world. The plant was Lupinus albus, white lupin. What the archaeobotanists noticed next sits quietly in their paper. Lupin remains are scarce in excavation sites compared with written sources. The ancient world wrote about this plant constantly. Columella had already codified its importance in the 1st century. When manure is lacking, he wrote, sow lupins as a substitute. The literary record is dense with references, but the physical record is thin. What survived fire and 2,000 years of burial was only a fraction of what once existed. White lupin is an annual legume reaching roughly 4 feet tall. The leaves are compound, 5 to 9 leaflets radiating from the stem like an open hand. The flowers grow in upright clusters, white to pale blue. The pods form in groups of 3 to 7, each holding 3 to 7 large, flattened, pale seeds. Those pale seeds are what mattered. Inside them, 36 grams of protein per 100 grams, roughly the same density as soybeans. 19 grams of dietary fiber per 100 grams, more than double what soybeans carry. No trypsin inhibitors. Soybeans contain compounds that must be heat-treated before livestock can digest them safely. White lupin does not. The seed could be fed raw, and the roots did something else. They fixed atmospheric nitrogen through symbiosis with soil bacteria. Between 140 and 270 kilograms of nitrogen per hectare in some documented trials. They also formed specialized cluster roots that released acids into the soil, unlocking phosphorus from forms other crops could not access. Deep taproots, penetrating over half a meter, broke through compacted layers that decades of shallow-rooted cotton had cemented into hardpan. If a crop matches its competitor in protein density, exceeds it in fiber, eliminates processing requirements, and rebuilds the soil it grows in, standard market logic suggests it should expand. If that same crop was ritually significant enough to accompany Roman dead and structurally embedded in agricultural systems across millennia, its disappearance becomes harder to explain through agronomic failure alone. The conditions for persistence were met. The outcome was erasure. That gap is not botanical, it is economic. By the 1940s, something had taken shape across the American southern coastal plain. From Georgia through Alabama, Mississippi, and the Carolinas, cotton farmers were planting lupins. Not for harvest, for burial. They called the practice green manuring. The lupin would grow through the off-season, then be plowed under before cotton planting. What cotton had taken, lupin gave back. Nitrogen drawn from the air, phosphorus unlocked from the earth, compacted soil broken open from below. These were not subsistence growers experimenting with a novelty. These were cotton farmers, generations deep in a system that devoured soil fertility the way fire devours kindling. After a few seasons of continuous cotton, southern soils did not just decline. They stopped producing. And so the farmers planted lupins. White lupin, blue lupin, yellow lupin, all grown not to sell, but to turn back into the ground. The communities who farmed it were not named for the cash crop. They were named for the crop that made the cash crop possible. They called it the lupin belt. At peak, over 2.5 million acres of lupines were grown as green manure across the southeastern United States. 2.5 million acres. That is an area comparable to the total farmland of some American states. Not dedicated to a cash crop, dedicated to the plant that made cash cropping possible. The scale was not experimental, it was structural. Across Georgia, Alabama, Mississippi, the Carolinas, the same pattern repeated. Cotton in summer, lupin in winter, plowed under in spring. The farmers of the lupine belt understood something that would later be engineered around with a bag of synthetic fertilizer. A plant that fixes over 150 pounds of nitrogen per acre, while simultaneously unlocking phosphorus and rebuilding soil structure, was not an input. It was the foundation. And it was about to disappear. Not because it failed, not because something better arrived, but because the economics of American agriculture were about to be rewritten. And the crops that survived the rewrite were the ones with advocates in Washington. In 2017, a researcher named Przinsky published a synthesis consolidating decades of white lupin nutritional research. The paper drew on agronomic trials, amino acid profiling, and processing studies stretching back through the 20th century. What the data described was straightforward. Raw mature lupin seed contains 36.2 grams of protein per 100 grams. Soybeans contain 36.5 grams per 100 grams. The difference is 0.3 of a gram, a rounding error. The plant that was erased from American agriculture contains effectively the same protein density as the plant that was chosen to replace it. That alone should have ended the comparison. But the fiber numbers are where the gap appears. Lupin delivers 19 grams of dietary fiber per 100 grams. Soybeans deliver 9.3 grams per 100 grams. Lupin carries more than double the fiber. And there is the detail that feed formulators noticed decades ago. Sweet white lupin contains no trypsin inhibitors. Soybeans do. Soy meal must be heat-treated before it can safely be fed to livestock. An extra processing step, an added cost. Lupin does not require it. What this means in economic terms is not abstract. Nitrogen fixation reduces annual fertilizer expenditure at the farm level. No heat treatment requirement removes an entire processing infrastructure cost from the supply chain. Phosphorus unlocking through cluster roots reduces the input purchases that anchor commodity dependence. Each efficiency the plant offers eliminates a revenue stream for someone in the system. The crop that requires less becomes less valuable to the enterprises that profit from more. On July 10, 1954, President Eisenhower signed the Agricultural Trade Development and Assistance Act, Public Law 480. The legislation built an export pathway for American agriculture. The vehicle that drove on that pathway was soy. The legislation did not mention lupin. It did not need to. When you build a distribution system for one crop, every crop without access to that system falls further behind with every passing year. 2 years later, the Agricultural Act of 1956 went further. The law tied cottonseed and soybean supports to equal competition frameworks. Soybeans were written into the federal commodity architecture by name. They received price floors, export subsidies, institutional support from county extension offices to international trade negotiations. Lupin was not written in. And when policy decides which crops receive the architecture of profitability, the crops left off the list do not need to be banned. They simply stop being planted. Minnesota and Wisconsin extension data from 1989 showed soybeans exceeding break-even yield thresholds in 100% of reference trials. Non-irrigated lupin exceeded break-even far less often. The comparison was real. The conditions that produced it were not. An advocacy organization had been running for decades before any of this legislation passed. The American Soybean Association was founded in 1920. By the time Public Law 480 was signed, the association had spent over 30 years building market infrastructure, lobbying for favorable trade policy, and positioning soy as the default plant protein in American agriculture. No equivalent organization existed for lupin. Not in 1920, not in 1954, not today. What this means is visible in the data. Soybeans had received a century of breeding investment. Lupin had received almost none. Soybeans had a commodity futures market, a processing infrastructure, a global supply chain. Lupin had regional trials and extension bulletins that documented its performance, but no institutional memory to carry that knowledge forward. The crop was not defeated. It was defunded. Structural misallocation does not remain permanent when the underlying economics shift. In Freising, Germany, the Fraunhofer Institute for Process Engineering and Packaging developed protein extraction methods for lupin seeds. That research spun off into Pro-Lupin, which began placing lupin-based dairy alternatives in European retail by the mid-2010s. Soft cheese, yogurt, ice cream, milk alternatives. Across the English Channel, programs explicitly targeting reduction of soy import dependence began listing lupin cultivars and establishing supply chains. In Western Australia, state funding was allocated to wide open agriculture for lupin-enhanced oat milk production capacity. Australia grows a different species, Lupinus angustifolius, the narrow-leafed or Australian sweet lupin. Different species, same family, same recalibration. The breeding science caught up as well. For decades, the limiting factor was alkaloids, bitter, toxic compounds that made raw seeds dangerous. Classical breeding selected for low alkaloid sweet varieties. Recent genomic work identified the causal mutations controlling alkaloid biosynthesis at the DNA level. The most explicit institutional response may be legume generation, a multi-country research initiative running from 2023 to 2028, coordinated through Germany's Julius Kuhn Institute. Their target is quantified: 4 tons per hectare grain yield and 40% protein content in farmers' fields. White lupin is specifically included. This represents government-funded, institution-backed, deadline-driven research across multiple national agricultural organizations in Europe and Australia. The revival is not happening despite institutions. It is happening because institutions are correcting prior allocation patterns. What the lupin belt farmers implemented 80 years ago is now being reconstructed through formal research frameworks. If you want to find it, you need to know what you are looking at. The pale seeds are the key visual distinction. Ornamental garden lupins produce smaller, darker seeds. Those are not food grade and have caused documented cases of poisoning. 3 safety constraints are not optional. Only consume seeds from confirmed sweet low alkaloid cultivars. If you are not certain the cultivar is sweet, do not consume it. Lupin can cause allergic reactions, with particular risk for individuals allergic to peanuts. The European Union lists lupin among regulated allergens. Species confusion has resulted in modern poisoning cases. Source only verified food-grade Lupinus albus from reputable suppliers. Sweet lupin flour, lupin protein isolate, and whole lupin seeds are available through specialty food retailers and increasingly online. In Australia, lupin products occupy growing retail space. In Europe, the Louvre brand operates in multiple markets. In the United States, availability remains limited but expanding. Lupin flour appears in gluten-free baking products and protein supplements. Lupin flour substitutes into baking at roughly 15 to 30% of total flour for protein and fiber enrichment. Whole sweet seeds can be soaked and prepared like chickpeas. The flowers still grow in upright clusters, white to pale blue. The pods still form in groups of 3 to 7, each holding 3 to 7 large flattened pale seeds. Inside them, 36 grams of protein per 100 grams, 19 grams of fiber. Roots that still fix nitrogen and unlock phosphorus from soil that other crops cannot touch. A plant with protein density matching soybeans, fiber exceeding them, processing requirements below them, and soil regeneration properties absent in them was not agronomically defeated. It was structurally outcompeted through policy alignment, infrastructure investment, and institutional advocacy that favored a competitor. The American Soybean Association was founded in 1920. Public Law 480 was signed in 1954. The Agricultural Act of 1956 codified soybean supports. No equivalent structure existed for lupin. The comparison that followed was between a crop with a century of institutional backing and a crop with none. The revival currently underway in Germany, the UK, and Australia suggests that when institutions reassess allocation patterns, the agronomic logic that was bypassed decades ago becomes visible again. The lupin belt is not gone. It is being rebuilt under different institutional arrangements.